Hi, welcome to Intermolecular Forces, Solids, and Liquids. My name is Dr. English. Today we're going to be talking about liquid phase terminology. Specifically, we're going to be looking at critical temperature, critical pressure, vapor pressure, volatile versus non-volatile liquids, vapor pressure and boiling point, and normal boiling point. Let's start out by talking about critical temperature and pressure. A gas will typically liquefy or change from vapor to liquid at a certain pressure. As temperature increases, the pressure needed to liquefy a gas also increases. Above a certain temperature, no amount of pressure will cause a distinct liquid phase to form. So if I look at this diagram right here, if I go along and I look at an increase in temperature and I go up to look at what phases are involved, this down here is all the gas phase. And even though I might increase the pressure, there will come a point that even by increasing the pressure and trying to move particles close to each other, no liquid phase can occur. Instead, as pressure increases, the gas becomes more compressed, but will not go to a liquid phase. The motional energies of the molecules are greater than the attractive forces that lead to the liquid state, regardless of how much substance is compressed to bring the molecules close together. So what does this mean? This means that the particles are moving so fast that there's no way to force them close enough together to allow intermolecular forces to occur. The greater the intermolecular forces, the greater the critical temperature of the substance. And we can see that by looking at this chart down here. We have methane, ethane, propane, and butane. These are all alkanes. They are increasing by one carbon. As they increase by one carbon, we see that their molar masses will also increase. And we know that in substances that are relatively the same and have the same molecular polarity, as molar mass increases, the strength of your intermolecular forces will also increase. As a result, the critical temperature also increases. So while methane might have a critical temperature of 190.7, butane has a critical temperature of 425.17. So we can see this relationship between critical temperature and intermolecular forces. Critical temperature is defined as the highest temperature at which a distinct liquid phase can form or a liquid can exist. Critical pressure is defined as the pressure required to bring about liquefaction at a critical temperature. Liquefaction meaning the formation of a liquid. Vapor pressure is the pressure exerted by its vapor when the liquid and vapor states are in dynamic equilibrium. When considering a liquid, at any instant, some of the molecules on the surface possess enough kinetic energy to overcome existing intermolecular forces and escape into the gas phase. And we see that in this diagram right here. The weaker the attractive forces, the larger the number of molecules that are able to escape, and therefore the higher the vapor pressure. So we can see in this particular diagram is that as we add heat to solid neon, the particles are going to break apart, and particles and atoms from everywhere within the solid are now going from the liquid phase into the gaseous phase. And those particles are not coming just from the surface, but all the way through the substance. We compare that to water, which as a solid, we can see those intermolecular forces occurring. And then we add some heat, and we see it go to the liquid phase. But even as the heat's added, it's not starting to break apart. Here, as we add some more heat, some water molecules are being released, but really, typically, we see that only from the very surface of this liquid as represented in this simulation. So in a closed system, a point will be reached where the number of molecules escaping from the liquid phase and going into the gas phase will come into the equilibrium with the number of molecules moving from the gas phase back to the liquid phase. So eventually, the rate at which molecules return to the liquid exactly equals the rate at which they escape. At this point, the pressure becomes constant. We call this dynamic equilibrium, the condition in which two opposing processes are occurring simultaneously at equal rates. Now let's talk about volatility, vapor pressure, and temperature. When vaporization occurs in an open container, the liquid escapes Equilibrium is never established and the liquid evaporates until it's gone. Volatile liquids. These are liquids with high vapor pressures that evaporate quickly. Examples of these might be something like acetone and gasoline. We compare that to non-volatile liquids. These are liquids with low vapor pressures that evaporate slowly. So examples here might be motor oil or glycerin. As the temperature of a liquid is increased, the molecules move more energetically and a greater number can therefore escape. So as the temperature increases, vapor pressure will increase. Now let's talk about vapor pressure and boiling point. A liquid boils when its vapor pressure equals the external pressure acting on the surface of the liquid. At this point, bubbles are able to form within the liquid itself. The temperature at which a given liquid boils increases with increasing external pressure. So as we increase the vapor pressure, we can see the temperature at which these liquids boil will also increase. The normal boiling point is the boiling point of a liquid at 1 atmosphere. So 101.3 kPa is equal to 1 atmosphere. And the normal boiling point here is defined as the dotted line. So what did you learn in this tutorial? We went over the concept of critical temperature, critical pressure, vapor pressure, volatile versus non-volatile liquids, vapor pressure and boiling point, and normal boiling point. Need more help? Feel free to contact me. Have a great day.